All right, Chem class, let's go ahead and do a comprehensive review of the topics covered during this unit. So hopefully you'll be ready by Monday for the test. This is kind of a last-ditch effort just to make sure you guys understand the material, because the class that I was in, I think there was a little bit of struggle going on with certain concepts, and I just wanted to make sure that we can pull it all together and see if we can understand each part. This unit is all about why atoms bond, and let's kind of start off at the very beginning to talk about why atoms bond. Atoms bond for two reasons. One, the Octet Rule, and the other is the rule of zero charge, and I'll talk about each of those individually. So atoms will form bond for either one or both of these reasons. The Octet Rule is this. All atoms form bonds to try to fill their outer valence shell. This is usually 8 electrons or 2 if you're from the first period. So what I mean by that is if you draw the Bohr model of an atom, their valence shell is the outside shell. Now some atoms have 1, 2, or 5 valence electrons, but all of them want to try to get to 8, and they can go up or down to do that. There are 2 that only want 2 on the periodic table, and that's hydrogen and helium from the first period. The other rule is the rule of zero charge. Ions form bonds to become molecules that is neutrally charged. Positive atoms will combine with negatively charged atoms or compounds in order to cancel out their charge to become neutral. So here's kind of the bonding flow chart. There's 2 big types of bonds. There's ionic bonds and covalent bonds. Now you need to know which type is which, so we're going to start out there. If you see a metal attached to a nonmetal, that's an ionic compound. If you see a nonmetal attached to another nonmetal, that is a covalent compound. That is your key way of knowing whether it is an ionic bond or a covalent bond. And we're going to talk about each of these individually, starting with the ionic compound. So let's start with learning about how to draw ionic bonds. So we're going to learn 2 things. What does ionic compounds look like, and how do you write the formula? Don't worry about these page numbers. It's mostly for my class. I'm just kind of recycling an old presentation. So just ignore that. Let's talk individually about what do ionic bonds look like and how do you write the formulas for ionic bonds. So first of all, what is an ionic compound? An ionic compound is a compound that is formed between a metal, usually a positively charged metal, and a nonmetal, which becomes negatively charged. And what happens when they come together is they transfer electrons in order to fulfill or gain a full valence shell. So that's that octet rule. And then they stick to each other in order to neutralize the opposing charges. That's the rule of zero charge. So let's do an example. This is what a Lewis structure would look like of an ionic bond. Here we have sodium. If you recall, sodium is from the first group on the periodic table, that first column. Therefore, we know it has 1 valence electron. Now, chlorine is in the 17th group, or the 7th main group element. So it has 7 valence electrons. Now, if you think about what an ionic bond is, you know that these elements are going to transfer their electrons. But who's going to give their electrons and who's going to take it? If you guessed that sodium is going to give its electron and chlorine is going to take it, you'd be exactly right. When that happens, chlorine becomes full and happy. But what about sodium? I want you to maybe think about this. You can pause the video right now and answer this question, maybe write it down. I'll talk about it in just a second. But how has both sodium and chlorine fulfilled the octet rule after this transfer? Pause the video, see if you can figure it out. Did you pause the video? Try it out? Good, let's go ahead and talk about it. Well, if you think about it, let's look at what a sodium atom actually looks like and a chlorine atom actually looks like. If we were to take that sodium atom and cross out that first valence electron, that 1 valence electron, because remember, it gives it to chlorine, well, look, it actually goes down to a lower shell where there actually are 8 lower electrons. And so it becomes full. It gains an octet. Chlorine will actually gain an extra electron, and it will gain a full octet as well. So that's where we can kind of see that both of them have fulfilled that octet rule. So sodium plus chlorine, this is what's happening. Sodium gives its electron to chlorine, its valence electron specifically. And what happens to sodium's charge? Well, if you think about it, sodium was originally neutrally charged. It had the same number of protons and electrons. But when it lost an electron, remember, electrons are negatively charged. So if it loses that negatively charged electron, what happens to the charge of sodium? That's right, it becomes positively charged, specifically positively 1 charged. Chlorine used to be neutrally charged, but then it gained an extra electron, so what's its charge? That's right, if you said negatively 1 charged, you'd be correct. So if we have a positive 1 and a negative 1, how do these 2 things come together? Well, they cancel each other out automatically. The ratio is a 1-to-1 ratio. You only need one sodium and one chlorine, and they'll plot together, and you'll be and you get a compound. Here's our ionic compound that has a total charge of 0. So that's pretty amazing, and that's how ionic bonds work. Here's one for you. See if you can try to do this one yourself. Magnesium plus chlorine. Here, I'll even start you out. We have magnesium atom and a chlorine atom. Draw the Lewis structures to see how they go. Did you pause it? Did you figure it out? I hope so. Let's see if we can do it together. All right, magnesium has a valence of 2. I look at that on the periodic table. Magnesium is in the second group. It has 2 valence electrons. Chlorine, we know from before, has 7 valence electrons. And hopefully you figured out that magnesium will give one of its electrons to chlorine. But what about this extra electron here? What's it gonna do? Well, I hope you guessed, but it's going to need another chlorine to come in and take that electron from it. So in this example, we can't survive with just one magnesium and chlorine. We actually need 2 chlorines. And when those two come together, they form this compound, MgCl2. So Mg and 2 Cls combine to form a compound. Now, think about what the total charge of this is, right? So that's my next question. What ions or charges did each element form when they transferred their electrons? If you said that chlorine formed, or if you said that magnesium formed a positive 2 charge, you would be correct. It lost 2 electrons. It lost 2 negative electrons. Therefore, it became positively 2 charged. What about each chlorine? Each chlorine themselves are negative 1 charged. This chlorine is a negative 1 charge. This chlorine is a negative 1 charge. So if you have a negative 1 here, a positive 2 here, and a negative 1 here, what's the total charge of the compound when it comes together? Well, hopefully you're exactly right. It should be 0. So they'll come together to form a total compound charge of 0. All right, let's talk about simple ionic compounds. When they come together to form, how do we make them? So we're talking about how do you write the formula for simple ionic compounds? Well, again, thought prompt. Why do atoms transfer electrons, and what is the consequence when it happens? Well, you just figured out that when atoms transfer electrons, what happens is they get charged. Now, each atom, if you look at the actual valence, forms a different charge. Group 1 elements form a positive 1 charge. Group 2 elements form a positive 2 charge. The transition elements have various charges, and we'll talk about them in a minute. But group 3 elements form a positive 3 charge. Group 4 elements are positive or negative 4. This is group 13, group 14, group 15 is a negative 3 charge. The reason it's a negative 3 charge is because they have 5 valence electrons, and what they want is 8, so they're going to gain 3 electrons or gain negative 3 charge. These group 16 elements have 6 valence electrons. They want to gain 2 negative charges, so they're going to be negative 2. Then group 17, same thing. They have 7 valence electrons. They want to gain 1 negative charge. Group 18, or the noble gases, have a 0 charge because they're full. They have reached their valence. Sodium, argon, krypton, xenon, and radon all have 8 outer valence electrons, and helium has 2, and that's as much as it's ever going to get. So that's why those guys are special. The noble gases don't react because they're full. They've kind of completed themselves. So how do you write ionic compound formulas? Well, in order to write a formula, it's kind of like what we did before. They must be written so that the entire compound must follow the rule of 0 charge. So what do I mean by that? Well, think about magnesium and fluorine. Magnesium has a positive 2 charge and a fluorine has a minus 1 charge. How are these two supposed to come together? I mean, they can, they're opposite charges, but what ratio do we need of each? Well, if you said that we need 2 fluorines in order to cancel out the 1 magnesium, you'd be exactly right. So it kind of looks like this. We need 1 magnesium and 2 fluorines. When those come together, they're going to create a compound, magnesium fluoride, or MgF2. That is our compound formula, and that compound formula follows the rule of 0 charge. What about lithium plus nitrogen? See if you can figure out how to put these two together by yourself. I might recommend pausing the video. Well, if you've unpaused the video, let's go ahead and do this. So think about lithium. Lithium has a charge of +1. I'm going to use these puzzle pieces. This is kind of how I think of it in my brain. Lithium has a +1 charge. It kind of has one little jut here. Nitrogen, on the other hand, has a -3 charge. There's 3 places that can be filled with a negative charge. So looking here, how many of each do you need in order to get a full valence shell for both, as well as cancel out and follow the rule of 0 charge? Well, if you said you needed a total of 3 lithiums to cancel out the 1 nitrogen, you'd be correct. Now, what's the formula you write for this? Well, when they come together, you're going to write it as Li3N. How do you name ionic compounds? They're actually really easy. All you do is you take the metal name, you add it to the nonmetal name, and then change the ending to "ide." So in our 2 examples with magnesium and fluorine, when magnesium combines with fluorine to make MgF2, it's called magnesium fluoride. And lithium, when it combines with nitrogen, when we get Li3N, it's called lithium nitride. Naming ionic compounds, especially simple ones, are pretty easy. But what about ionic compounds with transition metals? Well, let's talk about how we name and write formulas with ionic compounds with transition metals. Again, you don't need to worry about this page number. That's for my class. I just want to talk to you about them. So there's a problem with transition metals that we kind of skimmed over before. Transition metals have variable charges. That means that their charges aren't always the same. In fact, they're quite different. We get some of them that have a positive 2 charge, some of them have a positive 1 charge. And we're talking about single atoms like copper, for example. If you look on the back of your periodic table, if you have one that has a variable oxidation numbers on it, you might see in the very beginning that copper actually can be a +1 or a +2 charge. So how do we tell and what do we do with it? Let's talk about that. When you name ionic bonds with transition metals, or if you see ionic bonds with transition metals, the name gives away the charge of the transition metal. So ionic bonds with transition metals will use a Roman numeral in the name to designate the charge of that transition metal. So in our example of copper with a +2 and a copper with a +1, it would be written as copper +2, or like this. And it would be written as copper 1, or just copper if it's a +1 charge. So kind of the rule is if you see a transition metal and there's no Roman numerals that exist, just assume that it's copper 1 or whatever element that is 1. So here are Roman numerals just in case you don't know them: 1, 2, 3, 4, 5, and 6. This is probably as high as we're ever going to get in this class. So just make sure you know how to do Roman numerals. So just a quick thought prompt. Name the following compound and determine the charge of iron. I'll give you a hint. Start with what you do know. So this is kind of a hard problem. So you see we have iron and we don't really know what its charge is, and we have oxygen, but we do know what its charge is. Think about oxygen. Oxygen has a -2 charge. I'm going to use these puzzle pieces again. So this oxygen has a -2 charge. It's one piece of oxygen with -2 charge. How many oxygens do we have? We have 3 of them. Now irons, how many irons do we have? Well, we only have 2, so we're going to have to split our oxygens kind of in half and make 2 pieces to fill that side. What are the charges of each piece of iron? If you said +3, you'd be exactly right. So how do I name this compound? Well, if it's a +3 iron, I'm going to name it iron 3 oxide. Not iron 2 oxide. This is how many irons are in the compound, and it is not the same as the charge of iron written in the formula. So naming iron 3 oxide. So if you have an atom with a transition metal, it's named the same, except you just need to include the charge in the element and used in Roman numerals. Okay, let's talk about polyatomic ions. These are really kind of challenging because I think a lot of people don't understand what a polyatomic ion is. So we're going to talk about how to name and write formulas of ionic compounds with polyatomic ions. A polyatomic ion is this. It's a group of combined atoms that have an overall charge when as one combined molecule. So this is a phosphate ion, this PO4 right here. Now this PO4 is considered to be one piece, even though it's made up of both phosphorus and 4 oxygens. But this piece, phosphate, PO4, has a total charge of -3. Similarly, this hydroxide, OH, that's 2 odd atoms. That's a polyatomic atom. But this one this one molecule has a piece that's a -1 charge. So if you go and check the front of your periodic table, you have a list of polyatomic ions that kind of look like this. Now these pieces right here have a +1 charge. All of these ones here have a -1 charge. These ones have a -1 charge. These ones have a -2 charge, and these ones have a -3 charge. So just so you know where we're coming from there. And these are polyatomic ions, or groups of atoms that overall together have a charge of -1. So I really want to quickly introduce to you what happens when you have a regular ion versus a polyatomic ion. So what if we took aluminum and added it to each of these ions? Let's look at our first example here. Aluminum +3 plus selenium, which is a -2 ion. If you form those together, then you need 2 aluminums in order to cancel out, and you need 3 seleniums in order to cancel them out. 2 aluminums gets a +6 charge, and 3 seleniums gets a -6 charge, so that cancels each other out. How about this polyatomic ion here? This is a sulfate. Now remember, this piece right here, I'm not going to do anything with this. I'm not going to foil in the -2. I'm not going to worry that oxygen has a -2 charge and sulfur has a -2 charge. This charge has nothing to do with the individual charges of sulfur and oxygen. But when they come together, they form a special polyatomic ion that has a -2 charge. How do they go together? Well, they come together exactly like selenium. I mean, think about it. Aluminum with a +3. If you add 2 of those, you get a total charge of +6. Now, sulfate has a -2 charge. So if I had 3 sulfates, then I get a -6 charge total for sulfate. And those cancel each other out. So that's how I go ahead and combine and make polyatomic ions. So it's this last one kind of gives us an example. It's really just the same thing. This is just the general -2 ion. It could be a regular atom or it could be a polyatomic atom. All I do is basically do Al2X3, where the X could either be a polyatomic ion or regular ion. They're both the same. So how do you name atoms with polyatomic ions? Well, instead of changing the name to having an ending of "ide," you just use the ending or the name that was written as a polyatomic ion. I'm just going to pull the information from the periodic table. So right here, this NH4 right here, there's my polyatomic ion, followed by chlorine. That polyatomic ion, NH4, is called ammonium. So I'm going to go ahead and name this ammonium chloride. Now down here, I have BeNO32. This is my polyatomic ion right here, my NO32. I needed 2 NO3s because Be has a +2 charge and NO3 has a -1 charge. So I need 2 of those to cancel out my 1 Be. Now how do I name it? Instead of being beryllium nitride or anything like that, this is beryllium nitrate, and that's just the name I pulled directly from the periodic table. So that's really easy. Just pull the name from the periodic table. So really quick, thought prompt. How are sodium phosphate and sodium phosphide written differently? Well, sodium phosphate is a polyatomic ion. And if I go ahead and look at my polyatomic ion list, phosphate has a -3 charge. So sodium phosphate is written like this. Na3PO4. So PO4 phosphate has a -3 charge. Sodium is a +1 charge, so I need 3 sodiums to cancel out that phosphate. Now what's sodium phosphide? Well, ide is normal. That's what we're normally used to. Phosphate and phosphide are different. Phosphide is just the element from the periodic table. So sodium phosphide would be Na3P, because the charge of P, or the charge of phosphate, is a +3, and the charge of sodium is a -1. Okay? So that's the difference between the two. So I'm going to go ahead and erase this. Sorry, I wish I knew how to do this faster. This is new to me. All right, extra thought prompts. So thought prompt number 1, why are they called ionic compounds? Kind of really ridiculous, but think about the word ionic. Ionic means an atom with a charge, and they're called ionic compounds because we deal with atoms of opposite charge. So we have positive metals combined with negative metals. So here's a thought prompt 2. This is kind of combining everything you know. The rule for naming ionic bonds are metal plus a nonmetal and an ine. How does this differ if we have transition metals? And how does this differ if we have polyatomic ions? Well, if you said that transition metals must include Roman numerals for the metal, you would be correct. And for polyatomic ions, the only rule is if the polyatomic ion is a non-metal, if it's the anion, that don't change the ending to "I", just use the name found on the periodic table for polyatomic ions. That's the only different rule there. All right, let's talk about covalent compounds. So going back to our flowchart, we've talked a lot about metals and nonmetals, and those are ionic compounds. Now I want to talk to you about covalent compounds. Covalent compounds are between two nonmetals, or a nonmetal and another nonmetal. So we're going to talk about two things. What do covalent compounds look like, and how do you write the formulas for covalent compounds? Again, don't worry about these page numbers. They have nothing to do with your class. So why do atoms form bonds? We kind of need to remind ourselves what's going on here. If you recall, atoms form bonds to either fulfill the octet rule to get a full valence shell, that's what that means, of 8 or 2, or they form bonds to cancel out their charge. Well, covalent compounds are special. They don't need to cancel out their charge because they're both between nonmetals. So a covalent compound is a compound between two or more nonmetal atoms. Now, all nonmetal atoms are negatively charged, so they can't cancel out their charge. They have to find a different way to form bonds. So what do they do in order to do that? They're not following the rule of zero charge. Instead, what they're doing is they are fulfilling the octet rule by sharing their electrons. They don't transfer electrons to create charge. They share their electrons so they don't have to become charged. So let's see what we mean by that. So here's the Lewis dot structures for covalent bonds. Here is a carbon atom. If you recall, carbon has 4 valence electrons. How many does it want to fill its valence? Well, if you said it wants 8, you'd be correct. So it needs 4 more. Now, hydrogen, on the other hand, hydrogen is kind of special. It's from the first period, and if you recall, the first period only wants 2 to fill its valence. So hydrogen only really needs 1 more. So what are they going to do? These guys are going to come together and they're going to share. So carbon is going to come in and share its 1 electron with hydrogen. Now, hydrogen, I kind of created this Venn diagram, is sharing this black electron with carbon. And so it becomes full. It becomes happy with a valence of 2. Now, carbon with just 1 hydrogen isn't happy, so it's going to go find 3 other partners along with its original hydrogen partner, share with them as well, and it's going to become full. So all the partners here are happy with their full valence or octet. So look here, what's F going to do? What's fluorine going to do? We have 2 fluorine atoms, and this is an F2 or covalent compound. It's between a nonmetal and another nonmetal, or itself. What's going on here? Well, fluorine has 7, and this fluorine has 7. What can they do to combine and fulfill that octet rule? Well, they can come and share their electrons. So this fluorine is going to share its electron, this fluorine is going to share its electron, and they're going to come together in this kind of Venn diagram sense and share their electrons. This right here, by the way, is known as a single bond. A single bond is when 2 atoms, so here's 2 fluorines, share 2 electrons in between them. So one of them shared by one of them shared by the other. Now, this is usually written as a single line, kind of like this. Now, another thing I need you to know is the difference between these types of electrons. These electrons out here are called non-bonding electrons, where these electrons in here, the ones in the middle of the Venn diagram, are called bonding electrons. They're the ones that are being shared. So just so you know that. So drawing covalent bonds takes kind of a step. Step number 1 is sum all the valence electrons. Make sure you know how many valence electrons that you get to work with. Number 2, write each element symbol. Be symmetrical. Number 3, connect all atoms with 2 electrons to begin with, and then use up all the rest of the electrons to fill the octet rule. Number 5, you can steal pairs of electrons from the rich and share with the poor if needed. Let's try that out with this. So here we have O2. So I'm going to go ahead and start off and say, okay, we have O and O. Now, step number 1 says, how many total valence electrons do we have? If I look on the periodic table, each oxygen gets 6 valence electrons. So 6 plus 6 is 12. I have 2 oxygens, so I get 12 total valence electrons. So I have 2 oxygens. Now, the second thing it says is to write down the symbols, and I already did that. So here's 2 O's. Now, I need to go ahead and bond these two. So I'm going to add an electron between them and create a bond. So here's my first bond, and here's my second bond. So oxygen is bonding with this oxygen. They're sharing 2 electrons. So I'm using up 2 of my electrons to create a bond. So now I have 10 left over. Now I'm going to go ahead and fulfill my octets. I get 10 electrons, so I'm going to go ahead and just choose one. 1, 2, 3, 4, 5, 6. And then this oxygen's full. 1, 2, 3, 4, 5, 6, 7, 8. That oxygen's done. So I've used 6. That leaves me with 4 left over. So I'm going to come over here and do 1, 2, 3, 4. Well, unfortunately, this atom isn't happy, so I'm not really done with this octet, even though I'm done with this one. So the final rule says I can go ahead and steal from the rich. So I'm going to go ahead and steal 2 electrons from the rich, and I'm going to share them in the middle with the poor. Now look at this. I have a full octet here, and I have a full octet here. This one has 1, 2, 3, 4, 5, 6, 7, 8, because it's sharing 4. And this one has 1, 2, 3, 4, 5, 6, 7, 8. That one's done. So this is how I go ahead and create a covalent bond between 2 oxygen molecules. And it would look something a little bit more, excuse me, I'm going to erase this. It would look something a little bit more like this. So here's what it looks like. Now this is known as a double bond right here. When 2 atoms, 2 oxygen atoms, for example, share 4 electrons in the middle, and it's usually written as a double line. So think of these as kind of 2 lines. This is a double bond. See if you can figure out N2 by yourself. If you figured out this, then you're well on track. This is what nitrogen would look like, or N2. So this is known as a triple bond, when 2 elements share 6 electrons. So 2, 4, 6, 3 are shared from each. And this has happened so nitrogen can fulfill its octet. See, 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen is full. 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen is full as well. So each nitrogen has fulfilled its octet, and we have a triple bond shown like this. So try this one. This one's kind of a more challenging one. See if you can figure this one out. This is CO2. Pause the video. See if you can follow these tips and figure this one out. Did you pause it? If so, great. Let's go ahead and try this one out together. So here we have CO2. So I'm going to go ahead and count all the valence electrons. Carbon, I know, has 4, and oxygen each has 6, and there's 2 of those. So I'm going to do 6 plus 6 plus 4. So that's 12, 13, 14, 15, 16. So we have 16 total valence electrons to work with. Next, I'm going to draw the symbols. So I'm going to do it kind of symmetrically. I'm going to put C in the middle, and I'm going to put O on each side just to be symmetric with my elements. So now it says to connect them with a single bond. So I'm going to connect this one with a single bond and this one with a single bond. And here's where that looks like. There's that one. There's that one. And there's that one. Okay, so I've so far used 4, so I have to subtract 4 from my 16. That leaves me with 12 left. So I'm just going to start filling and making sure everybody's happy with an octet rule as much as possible. So I'm going to do that to this oxygen over here. 1, 2, 3, 4, 5, 6. That one's happy. Then I can do, let's do this one just to be symmetrical. 7, 8, 9, 10, 11, 12. There, I've used all of my electrons. Is everybody happy? Well, my 2 outside oxygens are, this one has 8, and this one has 8, but my carbon's not quite happy. So my last part, 5, my rule 5 says I can, or my tip 5 says I can steal from the rich and share with the poor. So I'm going to go ahead and steal these 2 and share them with the poor here in the middle. So oxygen's still happy, carbon's closer to being happy, but it's not quite happy yet. So I'm going to steal 2 more from oxygen over on this side because it's the richest, and I'm going to share it with the poor. Now I have a completed happy atom, okay? So there, that's awesome. I'm gonna go ahead and erase all this just to get to the next page. So here is what all that looked like. Here's CO2, there's my added electrons, this is what our molecule looked like, and this is actually what it looks like right there. All right, so how do you name covalent compounds? We want to talk about naming covalent compounds. So we see what they look like. Let's talk about how to name covalent compounds. Both there's regular ones and there's special ones called diatomic covalent compounds. So really quick thought. Is there more than one ratio combination of NaCl? Well, just to answer it really quickly, no. Na and Cl can only come together like this, Na and Cl. The reason for that is because of their charge. The rule of zero charge kind of prevents them from doing anything else. They can only be Na with a +1 charge, Cl with a -1 charge, and their ratio is a 1-to-1. But how about C and O? Well, maybe you know that there's carbon monoxide, there's carbon dioxide, and there's also a bunch of other types of ways to combine this. So the idea here is in ionic bonds, there's only one way to write an ionic bond. But for covalent bonds, there might be lots of ways to write covalent bonds. And so that's why covalent bonds are named a little bit differently than ionic bonds. So let's talk about how to write the name for covalent bonds. It's actually pretty easy. Covalent compounds use a special prefix before each element to determine the number of atoms present in the compound. And then, just like ionic bonds, they end in "ide." So this list, by the way, if you have it, is on the back of your periodic table. You might want to check. But here's the list right here that you can kind of write down. So 1 is mono, 2 is di. So 1 mono is like a monocle, like a one-piece eyeglass. That's where that comes from. 2 is di. Divide is made from the word divide, meaning to cut in two. 3 is tri. You guys have probably heard of a tricycle. 4 is tetra. The pieces from the game Tetris actually all have 4 pieces in it, which is why it was named that way. And then the rest of these are probably some type of polynomial shape that you guys are used to, like pentagon, hexagon, heptagon, octagon, nonagon, and a decagon. There is one exception to naming covalent compounds, and the one exception is this: you never name the first element in the covalent compound with the prefix mono. Never use mono for the first element in the covalent compound. So here's some examples here. How would you name this first one? Well, you're probably used to it. It's carbon dioxide because there's 2 oxygens and 1 carbon. Notice that we don't use mono here for carbon because it's the first element and there's only 1. So it's carbon dioxide. How about this second one? This one is carbon monoxide or monoxide. That means 1 carbon and 1 oxygen. How about this third one? Use your prefix list. Did you say dicarbon pentoxide? You'd be exactly right. There's 2 carbons, so dicarbon pentoxide. Now we can keep going. The next one is dinitrogen monoxide. This one should be, sorry, this is actually incorrectly written. It should just be nonoxide, not no-oxide. So nonoxide. The next one is NO2 or nitrogen dioxide, and the last one is nitrogen oxide, or this one would be nitrogen monoxide. Again, sorry for the mishap there. A nitrogen monoxide. Some molecules do have what I call street names. That's not really what you call them, but you're used to seeing things like H2O. H2O is water, but think about what it's actually called. It's called dihydrogen monoxide, and that's an okay name too, but we're used to calling H2O water. NH3 also has a street name, ammonia. There's other ones like chloroform. There's lots of street names out there, things that you might see on the side of a package that have names like this. So the last thing I want to talk to you about for naming compounds is diatomic covalent molecules. Diatomic covalent molecules are elements that don't exist in nature by themselves. There's certain elements that will never be by themselves in nature. So what they do is covalently bond to themselves and make an X2 arrangement. So here are the diatomic molecules. Hydrogen, right here. Hydrogen, for example, will never be found alone. It always bonds to itself. Nitrogen, whenever you hear somebody talk about nitrogen, it's really nitrogen gas, and it's N2. Oxygen is never found alone as oxygen atoms. They're always oxygen molecules, or O2. So I always remember these. Just remember 7 diatomicules make a 7 on the periodic table, starting at element 7 and including hydrogen. So starting at element 7 here, nitrogen, there are 7 diatomic molecules. You just make a 7. We don't go to the noble gases, so just make a 7 and then include hydrogen as part of that 7. And you'll remember that those are the diatomic molecules. The last thing we talked about was polarity intermolecular forces. You need to remember what electronegativity is. Electronegativity literally means an atom's ability to attract electrons. These guys up here on the periodic table have a higher affinity or a higher ability to attract electrons than these guys do down here. So fluorine has the highest ability to attract electrons. What that means is that some atoms, when they combine with themselves, such as H2, their electrons are shared evenly. You see this electron cloud is pretty even between the two. The distribution is the same. But some elements, think about HF, when these come together, there's an unequal sharing of electrons. Think about which one pulls the electrons in more. Fluorine, in this example, has a higher electronegativity. So it will pull electrons, the electron density around it will be higher than it would around hydrogen, even though they're supposed to be sharing electrons. Fluorine is just unequally sharing electrons. Now, when that happens, elements or molecules, when they do that, create this thing called a dipole. Think about a pole, like a north pole and a south pole, or the poles of a magnet. That's what a dipole is. It's kind of like that. It's a molecule that creates kind of like a magnetic pole where we have a partial negative end and a partial positive end. So there's a separation of charge. It's not fully separated charge, it's just partially separated charge because the electrons like to hang around fluorine over here. So you can kind of think of it like a tug of war where fluorine is pulling on the rope a little bit harder than hydrogen is and just creating a partial imbalance of charge. So nonpolar bonds like H and H or F and F, H2, F2 are equally shared electrons. They have equal electronegativity values and nobody's hogging those electrons. Polar bonds, on the other hand, have unequal sharing. Fluorine is pulling a little bit better on its electrons than hydrogen. Same thing with water, H2O. Oxygen is slightly more negative in charge because the oxygens hang around it more. It's better at pulling them in. So these are known as polar bonds. Why are we talking about these? Well, they're in order to talk about intermolecular forces. Intermolecular forces literally means forces between molecules. Inter means between. How do molecules interact with other molecules around them? There are 4 types of intermolecular forces: ion dipole, dipole-dipole, hydrogen bond, and induced dipole. And I want to talk about them individually. So ion dipole, pictures are worth 1,000 words, by the way. An ion dipole is where if we had an ion, such as a sodium ion, and if it interacted with a molecule that created a dipole. For example, water. If you throw sodium chloride in water, the sodium, the positive part of the sodium, would interact with the negative or the partial negative end of the dipole water molecule, and that creates an ion dipole interaction. This is the biggest reason why water breaks apart sodium chloride or table salt. It literally comes in, the negative, partial negative end of water will rip off the positive ends of the ion from sodium chloride. Think about that in terms of chlorine. If chlorine came in with a negative charge, the water molecules would flip around and the positive ends of the water molecules would rip off the chlorine. Next is dipole-dipole interactions. These are just where 2 polar molecules interact with one another, where the partial positive end of a polar molecule interacts or is attracted to the partial negative end of another polar molecule. So here's a dipole, there's a dipole. Hydrogen bond, I just want to let you know, is the same thing as a dipole-dipole. Here we have a molecule that has a dipole. There's a partial positive end here and a partial negative end up here. And here's another dipole where we have a partial positive end. Oh, you can't see that. Partial positive or partial negative end right here. And it's attracted to the partial positive end on there, and then there's a partial positive end down here. So a hydrogen bond is exactly like a dipole-dipole. The only difference between that is the hydrogen bond has hydrogen in it. So the hydrogen from one element, from one polar bond, is attracted to the negative, or the partial negative part of the other polar atom. And the other polar atom doesn't have to have hydrogen in it, though this one does. So water is a great example. The partial positive hydrogen atom from water is attracted to the negative partial part of the molecule of water here, and that's a hydrogen bond right there. The last one is an induced dipole. Induced literally means to persuade, and that's what that means. We can take a non-polar bond and persuade it to be polar by bringing it near a polar molecule. So this polar water is influencing this non-polar molecule by pushing its electrons away to the other side. Or we can do that oppositely as well. So an induced dipole is literally where we trick or persuade or influence them. That's it, guys. That's all we have. Good luck on your test for next time.